Hi, and welcome to another video in my series of videos about data warehouse and architecting and integrating data warehouse type workloads with hardware and software, particularly SQL Server, to have the most performant system. Now, if you have not done so, I highly recommend that you watch the subsequent videos to this video, as they are foundational and they will help explain in detail some of the concepts that I will be covering in this video. This video really brings together many of those concepts in such a way that you can start thinking about a data warehouse system in its whole and in its entirety, and many of those concepts will be employed here and discussed with this indexing video, because indexing is kind of the meeting point, the intersection of all these concepts that I've been covering. So this video will mainly be based on a series of demo scenarios where I talk about various indexing strategies and things related to indexing to consider. So without any more delay, I'm going to start with the indexing demonstration. Now, like in my previous demonstrations, I'm going to be using a test database where I have created a non-compressed table, a 10 million row fact table, and all it is a Cartesian join of the fact internet sales table from VentureWorks. So I try to use a common starting point for everybody, so anybody can emulate what I've done here in my videos on their own local PC with the VentureWorks installed in it. And up here here's some indexes I created. I just want to make sure they're not there for the first part of my video series here. So this should be a familiar query now for you if you have seen any of my previous videos. I'm not going to go over it too much. I am going to be querying again my non-compressed table. I'm going to be aggregating by sales territory and then summing the sales amount. So the only thing I've added here is kind of in my where clause I've added several predicate values. And this will come into play a little bit later on in the demonstration why I've done this. But if I go ahead and run this this query, now remember this table does not have any indexes on it. So what is occurring right now is that SQL Server has to do a scan of all of the data that's in that table. And so then now the data comes back, and as you can see from my sales territory column here, I have those predicate values aggregated up in that table. And if I flip over to my messages, as I have copy and pasted in my green area, my logical reads are 208,000 logical reads, and that represents 208,000 essentially data pages moving from disk to my CPU, and those are all the data pages for that particular table. So if you do the multiplication there that I've done in previous videos, you'll find out that that is actually the entire table's data. So nothing has changed there, 208,000 reads. What I want to talk to you a little bit more about this time is about the execution plan, because the execution plan will come into play here a little bit later on as I get a little bit more into these indexes. But if you look at and I kept this simple on purpose, because most of your execution plans will probably be a little bit more complex than this, but not very complex. Data warehouse queries, remember, are analytical in nature, so fundamentally in terms of execution plan and operators, you're doing the same basic thing. In other words, you're having a table scan, so you're scanning a table. Now I don't have any indexes created yet, so I have to do a full table scan. And then you're doing a hash matching operation, which then SQL Server has a few optimized operators for data warehouse workloads that it automatically uses, and that's good. So for these parallelisms and then the sorting and stream aggregates after that. What I want to focus in is this table scan operation. And let me move my screen over just a little bit so you can. Yeah, there you go. So you can see what's going on here. So my table scan, and if you look down, and you can see the actual number of rows, and the size and things like that. So this is and this goes back to my first video where I say that data warehouse workload is scan centric, right? So we're scanning things, and 208,000 rows. So also, as part of this, you'll see these green text right here that I have kind of my arrow over, that it's SQL Server has this feature that recommends an index. And here it says, hey, you know what? If you create an index, this will run faster. And so I'm going to go ahead and do that. I'm going to go ahead and create them. Now, I'm not going to use the recommended index that it has here, because the recommended index will be for this particular query. Now, in data warehouse scenarios, you most likely will have ad hoc queries, meaning the predicate values that you will be using, and even the columns that you specify in your predicate where clause will be different, will vary. And so creating one index will not cover all the scenarios. And so the best practices here, and this is talking strictly of non-Columnstore indexes, and I'll get to Columnstore indexes later, but if you do not have SQL Server 2012, then you are going to have to create what are called covering index. In a covering index, all that means is it's just a simple non-clustered index where you specify only one column. And so you're going to do that for every column in your fact table. Every column except for maybe your degenerate facts, like if you happen to have like a PO number, sales order number, line order number, those kind of things that aren't analytical in nature, but somehow for some lower level reporting you still need to grab that kind of stuff. If you happen to have any of that kind of thing in your fact table, make sure that you minimize those kind of columns as much as possible. But if you absolutely have to have them, then it makes no sense to create an index on them. You probably don't need an index. But for everything else, your surrogate keys and things like that, you will just want to put a covering index. So no include columns, no vertical partitioning, none of that kind of stuff. So, and I'm not going to create all the indexes because I'm just going to demonstrate one simple query here. But I am going to create the indexes required to make this query run a little bit faster. So I'm going to create an index on sales amount, and I'm going to create an index on sales territory key, because that was the column that I was calling out in my where clause there. So I'm going to go ahead and create those. Okay, great. Now that my indexes are created, and it took about a minute, I'm going to scroll down and run this. I just have the same query again. Again, it's this non-compressed table here, and here are my predicate values I'm looking for, and so I'm just going to run this query again. But this time the indexes have been created, and so instead of scanning the table's data, now the query can look and use the index data. And indexes data, for those of you who don't know, an index is just a copy of the table data. And as a copy, the copy of the data is, what the definition of the index is. The definition of an index, that definition, which column you include in your index is the makeup of that index's data. So, and if I go over to my messages, you're going to see, what you're going to see here is now something strange has happened. Well, not strange, but good. So my query now returns in 3 seconds, whereas previously I think it was something on the order of 13 seconds, 15 seconds, something like that. Now it's returned in 3 seconds. The reason for the dramatic decrease in time is because instead of reading the entire table's data, now the query can just read those two indexes' data. And the data represented or contained within those two indexes is just a subset of the total table data. And so what that amounts to is fewer logical reads, right? So it was about 200,000 logical reads for the entire table's data, and now for these indexes, now the total number of logical reads required for this to satisfy this query is about 36,000 logical reads. And if I click over to my my query plan, my execution plan here, what I get is now it has kind of a branch. So I have one main line and a branch, and if you see on the lowest branch here, this index scan. So no longer do I have a table scan, so now I'm scanning my index, and in fact I'm scanning the index here is the is one of the indexes I created above. So, and you can see that if you mouse over it there, this is the sales amount index. So, and if you see, beginning with the top there with physical operation, you have the index scan, and it's in row mode. That will come into play later. Remember that this is all row mode based, because these data pages, these table data pages, are stored data in rows. So in row-wise format. And I'll have an explanation of that versus the column store format later on. So fundamentally, what the database engine has to do here is, now that I've created those two indexes, it has to first decide whether or not it wants to scan a table or scan those indexes. In this case, the indexes are smaller. It knows they're smaller. It chooses the index. And so one of the indexes, it has to, out of the two indexes, it has to choose which one it's going to scan, and then which one is going to do kind of a hash match lookup against. So one of them is going to be your source index, and one of them is going to be your kind of your lookup index here. And so it has decided, based on statistics related to that index, that it's going to use this index, the sales amount index, to scan, and then it's going to do the lookup to the secondary index, the sales territory key. Okay, and then that matching occurs here, the hash match occurs here. That kind of lookup process occurs there. So that's why this query returns a lot faster than the previous query that was doing the full table scan. So again, the key to performance here is that throughput, minimizing the amount of data that has to travel through that throughput, because you are constrained in any data warehouse system to a certain throughput capability. All right, and so being able to minimize the data that travels across that becomes very important. So the less data you can travel across that, the more you can actually increase your currency as well. Meaning concurrency, sorry, not currency. Your concurrency, meaning the number of simultaneous queries that can be handled by the data warehouse. If you can reduce the size of the data coming across for those queries, then you can have more queries executing in your data warehouse and more concurrency, or bigger queries, either one. So again, and so I've gone ahead and looked up. So for this particular query, 287 megabytes were returned, and if you look at the sizes of the index, the sales amounts index was 212 megabytes, and then the sales territory key was 174 megabytes, right? And all that is much smaller than the total size of the table, and so scanning the index increases the speed of the query. So now what I'm going to show you is something that might at first seem illogical, but it does make sense. So here's the exact same query again. Now you won't be able to do this for your data warehouse in most instances. You can't control what predicate values or what columns they use to constrain the fact table on or filter the fact table on. Typically you can't control that, but I want to demonstrate why indexing, now this is talking about non-Columnstore indexes, I'll get to Columnstore indexes later, but why indexing only has a limited ability to improve your data warehouse's performance. All right, and it might not seem like, well, I should be able to just index for everything, and everything should just run real fast. If it runs slow, I just create more indexes. No, that's not an OLTP system. You couldn't maybe get away with that to a certain degree, but in data warehousing, you're kind of limited in what you can do, and the reason is because of the workload. So what I'm going to do is I'm going to take away half of the predicate values. So number 6 and number 7 there, I'm just commented out, and I'm going to run this query. Now what you would expect is that you would reduce the amount of logical reads by about half, let's just say, because if you go back up here to the query with the all 4 reading against the indexes, all 4 predicate values, I had 36,000 logical reads. Well, executing this query, if I take away half the predicate values, you would assume, well, maybe you have about half the logical reads. And in fact, no, that does not occur. It only drops by about 3,000 logical reads, which as a percentage of overall total of 36,000 logical reads is fairly small. It's nowhere near half, 50%. So why is that? Why don't these indexes have less data returned? Because I'm only returning half the predicate values. Well, that's, again, you have to think about the data warehouse workload here. My query plan is going to be virtually identical. I'm still scanning that same index. The sales amount index, and I'm doing a seek on the secondary index there. So all the operations are the same, and in fact, the reason why this query fundamentally executes in roughly almost exactly identical time is because SQL Server or any database engine still has to scan those indexes, and so the performance of this query is limited to the size of your indexes, and the size of your indexes can't really change beyond a certain point because they just have to hold so much data. Now this table is very small, it's only 10 million rows, but if you have billions of rows in your fact table and things like this, then you're really going to be limited. I mean, you need to put those indexes in the manner I described, but after that it's going to be very hard to improve the performance of those queries, because fundamentally what the database engine is doing is scanning those indexes. So no matter what again, most scenarios you can't control the predicates that get used or which columns are filtering the fact table by, but even if those change, that has little impact on overall performance of the data warehouse. Meaning it still will come back the query in about the same amount of time. So and just to further emphasize this, I'm going to limit the predicates here for this exact same query. Just commented out the fourth key value for the sales territory, and we'll run this query again. And what you're going to see, what I've copied up there, but going down to my messages, what you're going to see is now logical reads have only been reduced to about 30,000 logical reads. And so the moral of this story is, even though the number of predicate values I'm looking for in my index is a fourth, let's say, and I don't know proportionally the frequency of occurrences of these things, but you would guess something like that. This doesn't. So this just further emphasizes my point about indexes, that the indexes are good and necessary to increase performance, but fundamentally because you can't really reduce the number of logical reads beyond the size of your index, your performance will be constrained by the sizes of your index, or indexes. That's better said that way. So, and as I mentioned in a previous video, you can use page compression. So compression technology, and I explained it a little bit in the other video, can be used, and you can compress either table data or you can compress index data, or both of them. It's your decision, but you compress data on an object by object basis, so table, indexes, etc. And so what I'm going to do is I'm going to take my indexes and I'm going to compress them. Now I don't need to compress the table because my query doesn't really hit the table for the purposes of this query's performance. So you still want to, in the real world, compress your table data because then it'll just take up less space, and less space is better. You can fit more data on your data warehouse, but it won't necessarily increase the performance of your data warehouse queries because your queries don't hit the tables, they hit the indexes which hold a portion of the overall table's data. So I'm going to do that right now. I'm just going to rebuild the partitions with page compression set to on. Okay, now that my indexes have been created, I went back and I looked up the sizes of the indexes, and as you can see, they're much smaller. Previously they were, I believe, 200 and over 100 megabytes apiece, at least over 100 megabytes apiece. Now they're down to only 11 megabytes apiece for each one of them. So, and that's because of the page compression. And so naturally, hopefully you have enough understanding now that you can imagine now when I query these indexes, my number of logical reads is going to be even less because my index size is even smaller now with compression. And in fact, that's what happens. So, and because the size of the data of the table I'm working with here in these indexes is getting really small, I'm not going to see huge performance gains just given the size of these tables. But if you were to have much larger fact tables, you would definitely see a pretty significant performance increase in terms of your logical reads. They could be reduced as much by 3 to 5 times. So, and as you see, logical reads have been reduced from about 36,000 to about 20,000. So, and that will translate into faster query response times by using page compression there. Now, so what I'm going to do is, if I go over into my Object Explorer, what I'm going to do is I'm going to now create a Columnstore index. And what a Columnstore index is it is an index, but it is a completely different way to represent data. And so it represents data in a column-wise format. And I'll go in a future presentation, go into more details about how Columnstore indexes work and what their components are. But just remember that they are an index, but they store data completely differently. And they store data in a way that is really optimized for data warehouse type workloads. And so that's what I'm going to do. I'm going to create a Columnstore index here. Click Execute. Now again, I'm only creating a Columnstore index for 2 columns of my fact tables, the 2 ones I need for my query, but you would want to go ahead, there's a little bit difference here on the best practices for Columnstore indexes. You want to create one Columnstore index that contains all or virtually all the columns in your fact table. The only columns you may not want to include would be those degenerate fact type columns, those columns that have things like purchase order number, sales order number, those things which aren't really of any analytical value. You don't really do analysis based on individual sales orders or line order numbers, things like that. Those you can go ahead and leave out of the Columnstore if you wish. Because they are of no analytical value, and they just make the index a little bit bigger, and so it just takes up a little bit more space. So now that the index has finished being created, I can go over to my Object Explorer, and so for those of you who haven't seen one, here's my non-compressed table, and under my indexes, I now have 3 indexes. I have the first 2 indexes I created, and then I compressed them using page compression, and then now I have my Columnstore index, and that's what that looks like. Now, in your regular fact table, you would never want to have a Columnstore index and then non-clustered indexes in there. You just have one Columnstore index, and that's virtually all that you need. But for the purposes of this demonstration, this does have both kinds of indexes in there, just so you can see what they look like. So now if I run this again, this exact same query against my Columnstore index, you notice that the query comes back a lot faster, less than a second, whereas before it was 3 seconds. Now this table, again, isn't very big, only 10 million rows, and so it isn't a very dramatic performance increase. You see much more dramatic performance increases on the order of 10 to 15 times with much larger tables, billions of rows. And the reason for this, that it came back a lot faster, is because this is a data warehouse workload. It's because of the number of logical reads. So that is the fundamental reason why this came back so much quicker. This analytical type query came back so much quicker because now logical reads have been reduced to, in this instance, 154. Remember the original table was 280,000 logical reads, and then with the indexes, it was, and even a compressed index, it was 20,000 logical reads. Now with the Columnstore index, that goes all the way down, dramatic decrease to 154 logical reads. Which, yeah, when I ran it previously, it was 136, but when you do the multiplication, it's only about a meg, less than a meg actually. So now what I want to demonstrate, and because the 10 million row fact table was a little too small to make this point really clear, what I want to leave here now with a very important part of Columnstore indexing. And not only is there dramatic performance increase like I just showed you with the number of logical reads, because it's kept in a column-wise format, but there's a thing called segment elimination, and segment elimination is very key to understanding why Columnstore indexes will have tremendous performance increases if they're used right in a data warehouse type workload. Segment elimination, I'm not going to go too much into the structure of Columnstore index, that's for a future video, but segment elimination essentially means instead of what happened before with my regular indexes, where I had, no matter what my predicate logic was, I had to scan that whole index, segment elimination essentially eliminates that. So no matter how large your Columnstore index is, because your Columnstore index will get larger as your table gets larger, right? Because it's just an indexed version of your table's data. No matter how large that gets, you don't have to scan the whole Columnstore index. It's intelligent enough to eliminate those parts of its index that it doesn't need to satisfy its queries. What this means is that as you change your predicate logic, then literally the amount of data that comes back from disk is already pre-filtered in a way, right? Because otherwise what has to happen on your operators that I showed you in the query execution plan is that all this data has to be scanned from the index, then it has to go through a few operators and be filtered out, because SQL Server doesn't know what's on those data pages until it comes back and it can actually filter that to match your query's criteria. With Columnstore indexes, that changes. With segment elimination, literally the data that comes back is only the data, or for the most part, only the data that's required to satisfy your index, your specific query. What that means is you can change predicate logic, and actually the amount of data that comes back from your disk will change as well. So, and what I've done here is modified the existing query a little bit. So now I'm going to use a 100 million row fact table because this really demonstrates this a little bit better. And I'm going to choose a slightly different granularity in my query. I'm going to use due date here because the date has enough low-level granularity to it to really show off this kind of feature. And again, I'm still doing an aggregate here. So now if I were to run this with all four predicate values and execute it. Now this table does have a Columnstore index on it because I'm demonstrating a feature of Columnstore index. And so something very important happens because it is a Columnstore index that I'm now using. Let's see, move it over a little bit. What you see now, instead of, I'm still scanning my Columnstore Index, but if you look at the execution mode there, it says batch, starting on the third line down. Batch is very important. And I'll get into more of it later in subsequent videos, but this batch mode is critical to getting, when a Columnstore Index is used for a data warehouse query, it's always going to be used in batch mode. So there you go. So fundamentally what's happening here, it looks very much like my original query I started out with, in that I have a query index scan in this case, and then a hash matching and parallelism and sorting and just cleaning up the data to match whatever my projection or my select is. So, and if I go to my messages, now I have 236 logical reads. So, and this is pretty incredible in and of itself, that a table that is literally, I created this 100 million row fact table the same way I did the 10 million. It's identical, it's just 10 times as big. This table that's 10 times as big only has 236 logical reads. That is pretty profound. Instead of, it would normally have about 2 million logical reads had I used a regular non Columnstore index on this. So, and in my previous videos I demonstrate this as well. Now what I'm going to show you is the segment elimination. So I'm going to eliminate half of the predicate values. Now, when I did this previously, it didn't really change the amount of data that came back. It didn't change the number of logical reads. But now, because this is a Columnstore index, it is going to change dramatically, and it's going to be about half. So if I go to my messages here, it was 236 previously. Now it's 126, right? Roughly a half-fold decrease in the amount of data that came back from my disk. In other words, Columnstore Index is able to only pull the data it needs. The SQL Server can now just pull across the data it needs. It doesn't need to scan nearly as much data, depending on your query predicate logic. And if you go back to the query plan, that's exactly the same. And again, make sure it's in batch mode. Those kind of things means it's using the Columnstore Index. So, and in fact, if I do this one more, and now I just have one value for my column, my due date column predicate. Now if I just have one value in there, watch what happens. It was 126 with half of the predicate values, originally 236 or 230 something. Then I have the predicate values and it have the logical reads into 126. Now I'm going to do that again. And now look at my logical reads. They went from 126 all the way down to 15. And so this is the power of segment elimination. And so when, and maybe for those of you who haven't worked in very large data warehouse environments, it's hard to understand the value of this. But what this means is that for data warehouses in the order of tens to hundreds of terabytes and above, is that no longer are you scanning nearly as much information. And this really comes into play with and I'll go into this in future videos, with Microsoft's Parallel Data Warehouse that I have been working with off and on for the last 2 years. Now with Parallel Data Warehouse 2012, because it has Columnstore indexes in it as an available option, you can use those, and that can dramatically increase, and it really becomes a game changer in terms of how you set up the architecture for your overall BI solution. You don't have to do aggregates anymore, whether those be aggregate tables or whether those be OLAP cube aggregates in traditional multidimensional form. No longer are aggregates required, which saves a tremendous amount of processing and makes things like real-time data warehousing or near real-time data warehousing much more viable solution. So that is, and I'll go more into detail on that kind of stuff later, but hopefully this gives you a good foundation for understanding these principles. Of course, I'll have links to these scripts at the bottom of this video. And thank you for your time. I hope this excites you as much as it does me. Makes my life much easier as a data warehouse architect and developer. Thank you.